Hi everyone. Can you hear me?
Yes, he is audible.
Yes. Okay. We'll just get started now. To just tell you what we plan to do in the session. First one, I'm Varun, and I'll be taking this help session along with Aditya. First, we're going to be taking our quizzes and our midsem paper from our thermo course last year. We are both in S1, but I think I think the syllabus matches. So I think these practicing these questions will definitely help in both sections. So you won't have to worry about that. First we'll start off with our quizzes, in which the majorly we're going to cover the energy balances and entropy balances, which I think entropy balances some people have a bit of trouble. So I think that we have one question that should clear things up. After that, I think we'll also go into that Maxwell relations and just like understanding how to really manipulate those to derive the different things. I think that's also a little tricky at times. You can just get stuck at a point. So I think we'll just try to give you a good roadmap for that, and then we can take any other concepts or questions that you would like to ask us as well. So we'll get started now.
Okay. So I hope that you guys can hear me. I'll get started with the first question from the quiz one that we had. So the first question is the energy balance equation can be written as. So this is the standard energy balance equation which you might have derived in class, and uh, there are a few questions which I have asked based on this. So um, uh, Yeah, okay. So the first question is explain the meaning of each term in the above equation. Here, the first term we have is um, du by dt. So du by dt, here u is the internal energy of the system. The next term is the m dot k u cap k. So u cap k is the internal energy per mole, and it is this term here measures the flow of internal energy due to the different streams into the system. Um, then the next term we have is the q dot term. Q dot is the flow of heat energy, like the exchange of heat energy between the system and the surroundings. The minus P dV by dt term is the work required to change the boundary of the system. It could either be via expansion or compression. The next term here is the Ws dot term, which is the shaft work. The shaft work could include different types of work such as stirring, electrical and magnetic, etc. And the final term is the m dot k PV cap k. So this is the energy added to the system while making the kth stream flow. This is basically the flow work. So now the next question that we have is the total work energy exchange between the system and the surrounding is given by. So this the answer to this question would be the following terms: p dv by dt plus ws dot, since shaft work is being done on or by the system, and there's the compression or expansion of the system that is given by the dv by dt term. The next question is the total energy brought into the system by the flow is given by. So basically this refers to the flow terms. So that refers to the flow of internal energies. So that is m dot u cap k plus m summation m dot k PV cap K. So these are the flow terms in the given equation. And then the next question is the total energy contained in the system is given by. So here the total energy contained is just given by the internal energy of the system, that is U. This is pretty straightforward. And the final question for the first question is, suppose the system were a piston cylinder arrangement, then the energy provided to the system for moving the piston is given by. So when you are moving the piston, you are basically compressing the system, or you could be expanding the system. So the term is given by minus p dv by dt, because this is the only term that deals with like the change in volume of the system. Uh, because the piston cylinder system basically deals with changing the volume of the cylinder. Then the next question we have is, um, so here we are given a steam table, and we have the values of molar volume, molar internal energy, enthalpy and entropy for different pressures and different temperatures. So the question that has been asked is, using the table given, calculate the thermal expansion coefficient for steam at 500 degrees Celsius and 0.1 megapascal. So so the formula for the thermal expansion coefficient, that is alpha, is given by 1 by V, uh, 1 by V cap, dou V cap by dou T at constant pressure. So this can be approximately written as 1 by V times delta V by delta T, and the values of uh, delta V and delta T, that is 1 by V1, V2 minus V1 upon T2 minus T1, and these values can be obtained from the table above, table given above. So in this case we can take the volume at 500 degrees Celsius for the V cap, and the delta we can take to be between the 600 and 400. So that would basically be equal to 1 by 7.134. So and that's this value here, and then we can do V2 minus V1, that would be 8.057 minus 6.209 by 600 minus 400 degrees Celsius. So this would give us a value of the thermal expansion coefficient as 1.3 into 10 power minus 3 Kelvin inverse. For the next question we have is, calculate the isothermal compressibility for steam at 500 degrees Celsius and 0.1 megapascal. So here we know that the formula of isothermal compressibility is given by K is equal to minus 1 by V cap dou V cap by dou P T at constant temperature. So we need to find this at 500 degrees Celsius and 0.1 megapascal. So we take the V cap to be same as before, 7.134. That's this value here, and then we take the delta V by delta P. So that will be around the 500 degrees Celsius, which is 3 3.565 minus 7.134 upon 0.1 minus 0.05. Because there's a delta P term here, we take the values from these two tables. So we take just a minute, we take this value here and this value here, and because there's a minus term here, we get the delta V as 3.565 minus 7.134, and there'll be a minus term over here. So and the delta P is basically 0.1 minus 0.05, and once we calculate this value, um, we'll get it to be approximately 10 power minus 5 Pascal inverse. So that is how you calculate the isothermal expansion coefficient and the isothermal compressibility. Basically, the two formulas that you need to remember is alpha is 1 by V cap, dou V cap by dou T at constant pressure, and Kt is equal to negative 1 by V cap, dou V cap by dou P at T. So you can refer to the values from the table given here, and then accordingly calculate the values. So the next question we have is, it's a continuation of the same question with the part C. That is, we have a 1 kg steam is contained in the compartment A, and 1 kg of steam is contained in B, as shown. The partition between them is removed so that the steam in two components can mix, and finally the temperature and pressure is uniform. So assumptions, the entire system comprising of the compartments A plus B is isolated. So isolated means that there is no change in the internal energy of the system. So du by dt would be equal to 0.
Just say 1 second, wait.
We'll wait for 1 second.
We don't calculate fully every time. It's taking time.
Fine. What should I do? Just
write the expressions. And
okay, fine. Okay, sorry for that. So basically, the assumption are the entire system comprising of the compartments A plus B is isolated. That's du by dt is 0. The kinetic and potential energy terms can be ignored. And this is another property that is given to us, that is theta cap can be written as theta naught plus whatever this expression is. So what we need to do is as we concluded that du by dt is equal to 0, and so we can do a energy balance on the internal energies. So that would be u cap tf pf times 2, that is 2 kg of steam, into is equal to u cap at 500 and 0.05 into 1 plus u cap into 500 comma 0.1 megapascal into 1. So from this you can calculate the value of the final u cap at the final temperature and pressure, and then we can use this relation that has been given to us here. So we what we need to find here is we know that q cap is approximately u cap at 500 degrees Celsius, comma 0.1 megapascal plus dou u cap by dou t at p naught t minus t naught plus dou u cap by dou p at t naught p minus p naught. So we know this value. We can find this value from the table. So we can take both these terms on this side and we'll get a value of 0.2 here. Like you can check using the values in the table and the value you can calculate from here. You'll get 0.2, and this value can again be calculated from the table, like for how we calculated the isothermal compressibility by taking a delta P by delta T. You can calculate it the same way, and T naught will be the 500 degrees Celsius and P naught will be 0.1 megapascal. So finally you'll get an equation of 0.2 is equal to 1.67 T minus T naught minus 8 P minus P naught. So this is the equation that you get from expanding the u cap term using this relation for the internal energy. Similarly, we know that another constraint would be that the volume of the system does not change with time. So we can use the same expansion of v cap as equal to v cap at t naught comma p naught and so on. So this will give you another relationship, and you'll get two equations and two variables. So you'll get one. This is the one equation that you got here, and you'll get another similar equation in terms of t comma p. You just need to solve for those t comma p since you have two equations, and that will give you the final temperature TF and PF for the system. Okay, so I think the next question that we aim to solve was already there in one of your tutorials. So should I still go about it? Like, should I still solve it? Could you repeat? Okay. Can you type in the chat? I can't hear you for some reason. Okay. So this is a bit lengthy. So what we'll do is we'll go over the next few questions, like the quiz 2 and midsem, and after we are done with it, I'll come back to this question. So hope that's fine. Okay. So um, I'll share. That's great. You'll have to open the file. Just keep the question and switch to that, I guess.
So that's the I need a new page. New page to
Bit.
Okay, so yeah, so now we're moving to our second quiz, in which we start moving into like combining energy and entropy balances. So screen is visible, right? Yeah. So in the first question, so we're given that it's a constant volume system. It's also isothermal, and it's a closed system. So when they say it's a closed system, what's that going to mean? That's going to mean there's going to be no flows. So m dot is going to be zero here. There's no flow of mass in and out of the system. So the first thing we've been asked to do is to prove that the maximum work is the sum of the reversible work along with T into generated entropy. So let's start. So let's first write an energy balance for this system. So now that we know that it's a closed system, so all the flow terms are going to be zero. So as we saw before, the energy balance, you're going to have the m dot into the internal energy. That term is going to be zero along with the flow work. So what are we going to be left with? You're going to be left with du, which is going to be u2 minus u1. That's going to be equal to q plus ws. Again, the PdV term becomes zero as it's a constant volume system. So now that's energy balance. Now the next step is going to be writing an entropy balance. So there, you know that ds is going to be q by t plus sgen. So now, what happened? It is muted. Huh?
Oh,
Okay, yeah. Sorry, I didn't realize it was on mute. Yeah, okay, yeah. Sorry, I'll just start over then. Uh, yeah. So let's just put it. So yeah. So again, now this first question. I just got started with it. So we're given that it's a constant volume system, it's isothermal and closed. So constant volume is going to mean that dV is going to be zero. Isothermal means the temperature is constant, and closed system implies that there's no exchange of mass. So that's going to eliminate the terms which we have any flow like m dot. If m dot is going to be zero here. So we're asked to prove these two equations here. So now to start off any question like this, you're gonna always try the energy balance first. I mean, I'd suggest in any question, always a good practice is starting with this energy balance based on the conditions in the question. So that's going to result in du is q plus ws. So how did I get that? So now all the flow terms are going to go to zero. The pdv by dt is also going to be zero. So all you're left with is u2 is equal to u1 plus q plus the ws. Now similarly, I wrote an entropy balance as well. So what is that going to give me? ds is going to be q by t plus sgen. Again, the flow term is going to be zero. So now in almost any question from after you write the energy and entropy balances, usually the next step in order to move forward to the other thermodynamic properties is going to be to substitute q in terms of entropy. So now how am I going to do that here? So q is going to be tds minus tsgen. So now I want to substitute this back in the first equation. Now I also know that let's see. Give me 1 second. So start with. So now once you substitute Q back into that equation, you're left with U2 minus U1 equals TdS plus Ws minus Ts gen. So I'm going to take it this side, U2 minus U1. Again, I'm going to expand ds as S2 minus S1, where S2 and S1 the entropies in the different states. So now you know that A is equal to U minus Ts, right? Similarly, you have the equation G equals H minus Ts. A is the Helmholtz free energy here. Now clearly from this equation, if you pair up the terms, you end up with an equation like this. So now you can easily substitute this as A2 minus A1 is equal to Ws minus Ts gen. Give me 1 second, there's some issue with the tab. Okay, one second. I think the screen looks frozen right now, right? Okay, it just okay. Okay. So right now, okay, is the screen, is the note visible? Okay, I just gave. Okay, so okay, looks like I lost the road till now. So I'll just, if you find, I'll just the session is being recorded, so I'll just continue from where I left off here. So we were at A2 minus A1 equals Ws minus Ts gen. So now we need to look at, in a reversible process, what's unique. So in a reversible process, the Sgen is 0, there's no entropy generated. So then Ws reversible becomes A2 minus A1. And now similarly from this above equation, we've ended up proving that Ws is Ws rev plus Ts gen. So I guess the main thing you just take away here are just, you should writing the energy balance and entropy balances under different conditions. I think your first thing is to observe what kind of system it is. If it's a closed system, that takes away quite a few of your terms. The flow terms are completely eliminated. Then similarly, if it's a constant volume, the PdV term is eliminated. So just identifying these keywords in these questions to simplify the balances is what you have to do in every question here. So now let's move forward to so in this quiz, there's actually a question in which there's a similar variation in the mid-sem. The one in the quiz is relatively simple if you compare with the mid-sem question. So I'm going to be solving the question from the mid-sem first. So and then you guys can try the question from the mid-sem after that. So the quiz. So let's move to the mid-sem. So I think it's visible. Yeah. So this is the question I'm talking. So this is the question I'm referring to here. So as you see here, there are 3 subsystems. The quiz question has a similar variation with 2 subsystems. So let's go over this question now. Yeah. So let's start. As you can okay, start this. The question. Okay, so let's go to the question first. So as you can see here, the overall system is isolated. So that means there's going to be no mass and no energy exchange. from the surroundings and the system. So now initially, you have the system at different conditions. You have T1, V1, N1, and similarly for the other cases as well. And let's go. Now at t equals 0, you remove the partitions. So now there is energy and material exchange within the subsystems, but you have to notice here that there's still nothing with the surroundings. So now now they've asked us what is the equilibrium condition for the entire system. So now we have to try to understand this in terms of the entropy, Helmholtz free energy, or the Gibbs free energy, depending on where our equation takes us. So now let's get started. So we'll start with the A and B part first. So again, this question also, first step, you're just going to have to write energy balance. So the total system is isolated. So the energy balance is quite simple in this case. Du by dt is going to be equal to 0 here. Here, U is basically summation ui, the sum of the internal energy of the three systems. This is for the overall system. Now similarly, and this is the first thing we have. Now let's go into the entropy balance. Again, for the entropy balance, it's still an isolated system. So again in this, it's going to be 0 here, plus Sgen. Because the Q by T term is going to go to 0 as there's no exchange of heat. And similarly, it's a closed system obviously, so m dot sk dot cap is going to go to 0 as well. So now, clearly, we know that Sgen is going to keep increasing until it reaches equilibrium. So what does that tell us about the system? That tells us that this is monotonically increasing and eventually it's going to reach a maximum. It's like something like this. This is not an accurate graph, but basically S is maximized, which is what we can take forward from this. S dot gen is just like a time variation of this. So now as you can see at the top here, I think he gave a lot of the relations that we had. Like for this paper, if you go up to the first page, so I think this is something you'll have to use quite well, especially in the exam when he gives it to you. So he gave us some basic relations with regards to U, H, A, and G, and then some basic formulae which is somewhat similar to these relations you saw while deriving these Maxwell formulas. So let's go back to the question. So I'm going to make use of the first thing, that was du is TdS minus PdV plus GdN. Okay, I think it's lagging a little bit. Yeah, give me 1 second. Yeah, 1 second, I'm just changing the connection. Just give me a minute. Yeah, so now just yeah, I think it's better now. Yeah, let me just continue. So now we have this du is TdS minus PdV plus GdN. Now we need to try to keep this equation in terms of the entropy, because we know that the entropy is going to be maximized. So that means ds by maybe du is going to be 0. I'll just get to that later. So let's take all the terms to one side except the entropy. So when you do that, you're going to end up with du by t plus p by t dv minus g by t dn is going to be ds, right? So I hope that's clear. So now, so what are the constraints on the system here? So now you know that this is isolated system, so the overall number of moles in the system is going to be constant. So now you know that means dn is going to be 0. That means dn from the first system plus total from the second plus from the third is going to go to 0. There is some exchange within the systems once the boundary is changed, but on the whole, the net inside the whole system, if you like draw a boundary around the three systems, like around 1, 2, 3. Let's see. Let's go back here. If you just draw a boundary here, nothing is going to go outside this boundary. So that's how I'm going to end up with this equation. Similarly, I'm also going to have dv1 plus dv2 plus dv3 equals 0. Like the system boundary is fixed here, it's not going to like explode, so I'm just going to keep this dv is going to be equal to 0. Then similarly, the total internal energy du1 plus du2 plus du3 is also equal to 0. Now so I'm going to use these equations. Like this is a manipulation. Once you solve one question like this, you will get used to it. So it's just a similar kind of thing everywhere. So if you feel like this is not very intuitive, that's fine. Like you'll do it once and you'll get used to it. So minus of du1 plus du2. Similarly, the same equations are going to arise for the other two equations as well. I'm not going to write them down here. That will probably just that it's. So I hope you got that. So now let's go into the original equation, which was this 8. So now yeah. So now this equation will split as du by t plus pdv by t minus gdn by t, right? And this is going to be applicable for each system. So for system 1, similarly for this system 2, and similarly for system 3. Now I got this relation here as du3 is minus of du1 minus du2. So I'm going to substitute that into this equation I got for total entropy over here. So now once you just simplify that, you can see that this, I'm going to write the whole expression here just to make things clear. So ds is going to be 1 by t1 minus 1 by t3 into du1 plus 1 by t2 t3 into tu2. Similarly, I'm going to have the same equations for the other terms as well. So I hope you guys can see like a pattern kind of forming here in terms of like the terms that we are getting. So once you, I think writing this would be a bit tedious here. So could you guys just confirm if you're like clear at how these equations are coming? Just type a yes in the chat if that part's clear. Got it. So now we know that the entropy is maximized. Okay, repeat. Got it. So so this part is this part clear? Like how I written this dn du along with, okay. So I guess, okay, this substitution, yes, I guess that's a bit tricky. So now let's just go into that once. So now if I substitute du3 as minus du1 minus du2, so let's go to the term for the third equation. So what is that term? So yeah, du by t plus p by t dv minus g dn by t. So for this is for the third system. So new page. Yeah. So if I substitute du3 equals minus du2 minus du1. So what am I going to get? So du3 by t3 is going to become minus du2 by t3 minus du1 by t3. Now in my original equations, what did I have? I had du1 by t1 and I had a du2 by t2 term. This is common for all the systems. So I'm going to pair up these terms now with d, like so. I'm going to pair up this and this. So I'm going to have du1 into 1 by t1 minus 1 by t3, right? And similarly, I'm going to pair up this term as well for the system 2 and 3. So I'm going to have du2 into 1 by t2 minus 1 by t3. Okay, yeah. So this part's a bit tricky, I guess. Yeah, it's for the first time. It's bit, even I think I remember I didn't think I saw this in the midsem either. So now that you have these relations, you know that ds. So let's just look at one term first. So this ds is du2 into 1 by t2 minus 1 by t3, right? So now this ds is going to be maximized with respect to all these differentials here. So that means du2 is not individually 0. So in order to ensure that this entire equation, like ds is du2 into 1 by t2 minus 1 by t3, similarly plus p2 by t2 minus p3 by t3 into dv2. So now I need this. So what I'm technically doing here is I'm just, since I know that the entropy is maximized, one second, I can write ds by du I equals, given that say the mole is equal to 0, similarly ds by dv1. So from these equations, all these terms in the brackets, this 1 by t2 minus 1 by t3, p2 by t2 minus p3 by t3, all them are going to go to 0. So if you write that entire equation, finally you'll end up just observing that that implies that the final temperatures of all the three systems are same. Similarly, the same for the pressures, and also the same for the Gibbs free energies. I think the temperatures part is fairly intuitive in nature. When once the temperatures are equal, obviously there's going to be no energy exchange, so that makes sense. And similarly, the finally there's no compression or expansion here when the pressures are same. So that is the first part of the question covered. Now let's go back to the top, and this is a minor variation. So the minor variation is the C part. Okay. So under, now we had two different conditions. Now you remove only the partition between 1 and 2, but that between 2 and 3 is only going to be it's like a closed system. There's going to be no mass exchange. So now this derivation is going to be identical in this case as well, especially with the first two systems. So yeah. So the only change here, I'm just going to write the minor modification. So now that we've been given that there's going to be, is it audible now? Okay, I think I just moved aside from the speaker. So now the only change is here. Now there's no exchange of mass from system 3. So that's going to mean individually for dn3, it's going to be 0. And similarly for dv3 is also going to be 0. This is because the partition between 2 and 3 is such that you can only allow exchange of energy. However, the partition between 1 and 2 is completely open, and there is both mass and energy exchange. So similarly, if you manipulate these equations as I did before, you write the energy balance, then you write the entropy balance, and then you write the overall internal energy of the system, du1 plus du2 plus du3 equals 0. you're just going to add that along with these equations. Here it's going to be dv1 plus dv2 is 0. You're not going to get the dv3 term here because that's individually 0 here. You're not going to get that. Similarly, dn1 plus dn2 is going to be 0 here. So that will slightly modify the final equations that you get. And similarly here as well, the entropy is still maximized. It's still an isolated system on the whole. So the energy and entropy balance on the whole is going to be identical. So in this case, you will only get you'll get the temperatures are equal for all three, and there is energy exchange. But in this case, if you go to the derivation, you're going to only get a P1 is equal to P2 and G1 is equal to G2. You guys can try this one yourselves. I'll also share the document with the solution as well later for reference. So this is, I think this question actually repeated in our quiz and midsem, at least for in S1. I'd say this is an important like concept in anywhere, so I don't see why it couldn't come in for S2 as well. So I hope this one is clear. So just give me a So now there's one more thing I'd like to cover myself here, and that is the Maxwell relations. I think generally in the exam it's possible to get stuck, I'd say, like while just writing those big derivations. So I'd like to give you like a good starting point in case you feel like you can unmute or you could type it in the chat. I think you better type it. I'm not sure if there's some audio issue I can't hear. It's not connected to headphones, right? I think it's an issue from our side at SM. Not sure. Okay. Now I think you can just try now. Try speaking. I think I fixed it.
Hello.
Yeah, it's audible.
Yeah. Okay. Can you go up to the question once?
Sure. Yeah.
In the A part of the question, they are asking what is the condition for full equilibrium of the system, and they are asking us we have to discuss it in terms of A, S, or G. So, like in the class, when we have talked about equilibrium, they tell us that A has to be minimized in equilibrium. If we want to reach equilibrium, A has to be minimized, right?
Okay. No, like that depends on the system condition. So in this case, I think that's another variation. So there would be certain cases in which A would be minimized, but in this case it is S which should be maximized. Let me just I think I have a question with me in which we can try to just understand.
No, I mean I think in the class sir made us write the definition of equilibrium as equilibrium of a system is defined as the point in time where Helmholtz free energy is minimized.
I think it's like it's both the conditions. It's the
Right, so-
entropy is maximized and the Helmholtz energy is minimized.
Yeah. So in this case, can we, when they've asked us to just write whether if they are reaching a maximum or a minimum, can we just say that A is minimized and we know that S is maximized because Sgen becomes 0, and we can write that ds by dt is Sgen dot, and that like ds by dt is Sgen dot and Sgen becomes 0. So we can say that S gets maximized, but and G has to be equal for all subsystems. Like instead of doing such a long derivation or working through the problem and telling that T1 is equal to T2 is equal to T3 and all of that, can't we just directly write that A is minimized and S is maximized?
Yeah, that answers the A part. But if you see like in the second part,
okay. About the B part, then we have to solve the entire thing.
So that's the point. So like from this energy balance, it comes out that S is maximized. The A minimized, they would require a slightly different way of moving about.
I mean, I don't know if sir made us write any condition for which A has to be minimized, but
I think it's under constant volume and temperature. Let me just actually try that once.
yeah, okay, okay.
See, look, yeah. So let's say we have a system which is closed, constant volume and constant temperature. Right. Oh, okay. There's someone is. Yeah, but still, I think I'll just go over it once. So it is a closed system, constant volume, constant temperature. So what's going to happen to the energy balance? So you have du by dt. Your flow terms are going to go to zero. Your PdV term is zero. And now what are you left with?
We have
You have
only Q and
Q dot.
WS dot.
Okay. Let's just ignore the shaft work for now while just doing this. Like so, and similarly for the entropy, your Q dot by T plus S gen. Now, if I substitute this equation here, I think you'll end up, if you substitute the Q value into here, you end up with d of u minus Ts by dt is equal to minus Ts
E
gen.
S gen dot.
Yeah. So this is going to keep now. This is a decreasing function clearly. dA by dt is minus Ts gen dot, and that's going to keep decreasing until equilibrium when it reaches a minima. So yeah, so at the A minima is under these conditions. This is a difference here. That it's a closed system here. In the other case, we are looking at an isolated system. So yeah, I think I've heard Manish. Yeah. So constant volume and temperature, then A is minimized. So I hope that's clear now. So just I'd say like carefully analyze the conditions in the question, write the energy and entropy balances, make the substitution for Q, and try to just observe what terms you can get, like U minus Ts. I think in a constant
So
pressure
like
system, yeah,
yeah, so like in any question, we basically write the energy and entropy balance, and then whatever we get from that is some like based on the conditions in the question. That is something we write. Like
yeah. So
in
from those equations, from this manipulation, you'll end up with a sensible like dA by dt is Ts gen. So from like basic calculus, you can understand. Okay, this is
yeah,
decreasing, and
yeah, yeah,
so
okay.
that's what you do. So I think for constant pressure, similarly, you'll get G is like
Yeah, constant
maximize.
pressure and volume. I think we'll get G is
Yeah,
minimum.
you'll get
Minimize.
H, minimize or maximize. I think that that's fine. So once I'd like to just touch upon this Maxwell relations, a couple of brief examples to just clear things up. So so almost all of them end up starting at this du is PdS minus PdV plus GdN. This is a pretty solid base. So let's just maybe go to how we get this. I think that would be useful here. So let me write an energy balance. Uh, du by dt. I'm going to write this for a molar basis. So n dot h plus q dot minus p dv by dt or v dot plus shaft torque. So this is an overall energy balance for my system here. Similarly, let's go into an entropy balance. N dot. So I'm going to have a q dot by t by t uh, plus h n dot. So now I'm just going to try to get rid of the time variation here. That's not that much significant. So if we just multiply dt, you'll end up with something like this: h dn plus q minus p dv. This is ws dot plus ws. Similarly, ds is sdn plus q by t plus sn. Now, as usual, you're going to want to substitute this q from the second equation into the first. I mean, almost, I'd say like, unless it's like a pure like entropy based question, almost everything, the point of the entropy balance is just to get this expression for q and then substituting it back here. So now once you do that, I know that TDS, just multiply T, so minus TS gen minus TSDN equal to q. So if I'm going to substitute this equation a into 1 here, I'm going to end up with du is h minus ts into dn in the right path, right? Yeah. Minus pdv plus tds minus ts gen. So again, that's basically what you want. I'm going to, like for a reversal process again, s gen would be 0. So let's just ignore that term. And this is what be g. So that's how you end up with this equation, TDS minus PDV plus GDL. And now moving forward from this, you can derive in. I assume he would give these equations in the exam, but moving forward, you can derive all the other ones from this. So you know H is U plus PV. Now differentiate du plus PdV plus VdP. You know du. So similarly, you get all the others. Similarly, G is H minus TS. So I know you know dg is dh minus tds minus sdt. You know dh. Now I just got to incorporate these terms. Similarly, a is u minus ts. dA is du minus tds minus sdt. So now I hope you like understood the flow here. Like that's what I want to emphasize on here, the flow of how you get all these equations that you're going to eventually have to use for these, maybe not exactly deriving Maxwell relations, but any sort of question involving like this kind of manipulation. Like I think you could just ask you, like there's quite a few variations in which you could go about framing a question here. So there's like a good general flow to keep in mind. And then along with this, uh, there were some basic calculus properties which you needed to use. I think one important, I'm just going to list some important ones here. I think you should keep this in mind. I'm not sure, do any of you have an open book exam or is it closed for both sections? Closed. Open for S2. Okay. Guruswami sir, open notes. Okay, that's normal. So closed. I think okay, closed. Okay, he will give you some relations in the exam, but I assume he won't give you these. So I think this will definitely help here. So the chain rule. So if you have this y is going to be the same, and you just swap this x and z. So this is very important. While for any sort of manipulation, I think this it's using this that you actually derive all the Maxwell relations. So in case they do ask you in the exam, I think that's definitely possible. Like he'll give you some basic information regarding these equations. This du is TDS minus PdV plus GDN, and then after that he'll probably give you, let me just give me a minute here. Maybe I'll just show one derivation for one Maxwell relation just to clear things up. Just give me 1 minute. I need to find the relations. I just one sec. Just give me 1 minute. We'll just find. I don't remember the relations. I need to figure out what to prove. Actual relations. Okay. So yeah. So let's just try to prove this. dt by dv at constant entropy is minus dp by ds at constant volume. Right. So okay, so I'd say like it's good to practice this once before. Like the initial approach can be a bit tricky. So just yeah. I just one thing I'd also suggest in chapter 6 of Sandler, they've like given some few examples here, like some illustrations as they derive some different relations. I definitely suggest to practice that once as well. So first, Yeah. So let's just look at this. Constant volume or entropy. So if you just look at this expression here, so du by ds at constant volume. So I'm going to assume there's dn is going to be 0 in all these. It's a closed system. There's no exchange of mass. That's going to simplify all these relations. So now if you go back to U equation, where is it? Let's just start. Okay. So du is tds minus pdv plus gdn. Again, this is 0. So du by ds at constant volume would be temperature. So what does this become? dt by dv at constant entropy. That's one thing you know. Similarly, du by dv at constant entropy is minus p. So dou by dou s at constant volume du by dv entropy is going to be minus dp by ds. Again at constant volume. So just give me 1 minute here. I'm kind of stuck for a second. Just vaguely remember these. Just give me 1 minute. Sorry. Maxwell relation. I'm getting stuck. How do you derive it?
dv. Otherwise, do one thing. I'll do my questions. You solve it.
Yes, we'll move forward to the next part here. I'll get back to this at the end. I'm just a bit stuck for a second. Sorry about that. So yeah, we'll just move forward with that question initially we had left from the quiz one.
Can you open that? Open it. No, don't open it here.
Can I ask something before you?
Yeah, you can ask. Yeah, you can move forward with any doubts also.
Yeah, I just had one question, no doubt, really. But like for real gases, when we have to derive these expressions, like we have that expression for du is that CVdt plus T times del P by del T V at constant volume minus P times dV. Like those relations,
Yeah.
using that, if we have to derive Maxwell relations for real gases, does that change? Like, is Maxwell equations valid for real gases as well, or is it like we have to derive something new?
Just give me 1 second. There, I see. Like when you're solving these equations, you're not really you're considering both the terms. Like when you will say u is a function of temperature, volume. So this is applicable for both real and ideal gases. Nothing changes. Like you might have to make use of all those equations as well to like derive it. Like combining all of them. Like you'll just have to like quickly analyze. Okay, I see this equation. What can I extract from this equation? Like if you have du is tds minus pdv plus gdn, I could probably extract du by ds. Like so, yeah. Like to specifically answer your question, yes, it's applicable for both. There's no specifics regarding ideal and real gases. If it's a real gas, then it's going to be only a function of temperature. A lot of these equations just become quite simple, but it is applicable for both.
I hope that's clear. Now we'll solve that question from the first quiz. So here we have been given a system where there's a piston where there's a weight, there's the sand of mass W on the piston, and it's compressing the air inside the cylinder. So it has been asked that I just read the question once. An initial pressure is maintained on the gas contained in the piston cylinder system by a pile of sand of mass W, and the mass of the piston is W, omega, and the surrounding atmosphere. Work is obtained by removing the sand in equal batches and allowing the air to isothermally expand, thus lifting the piston and the remaining sand. The process is repeated until all the sand has been removed. The piston has an area A. Assume that as a result of sliding friction between the piston and the cylinder wall, all oscillatory movement of the piston after the weight is eventually removal of the weight will eventually be damped. So basically, we have a system of we have a cylinder piston system, and on top of it you have sand of weight uh, hello okay sand of weight m, a piston of weight omega, and there's the atmosphere which is applying the pressure on this piston, and this is compressing the air inside the cylinder. So um, okay, so basically, since this is a constant temperature system, uh, that is T is constant, the internal energy of the system will not change, because um, because the temperature is constant. We are also assuming that the air inside the piston is behaving like an ideal gas, so the internal energy of the system will not change. That is, du by dt will be equal to 0. So performing an energy balance on the system, we'll get that u is equal to q plus w, and sorry, q plus w will be equal to 0. From this, we'll get that q is equal to minus w, and w is equal to integral v vi to vf pdv, uh, and this is assuming that the gas is at a uniform pressure. Then, using the since we have assumed that it is an ideal gas, we can use the ideal gas equation, that is PV is equal to nRT, to get that the heat uh, heat released in this system would be nRT ln Vf by Vi. So this is basically integrating this by substituting this in this integral. After this, we can uh, okay, so then we can calculate the final pressure of the system as given by the equation P atm, that is the pressure exerted by the atmosphere, plus W plus omega by A times G. So at any given point, W is the weight of the sand that is on top of the piston, and omega is the mass of the piston, and A is the area of the piston. So since the pressure exerted by the piston, uh, the final pressure will be equal to the pressure exerted by the piston plus the pressure exerted by the atmosphere, and we can write that P initial is equal to P atm plus omega plus W plus delta W by A and G. So this is the initial pressure, and this is the final pressure after you remove weight delta W. Um, okay. Here the amount of friction doesn't matter, and this implies that the final volume of the gas will be given again by the ideal gas equation, that is nRT by Pf, and we can find the Pf from this equation here. After this, uh, since we if for example, if the friction of the system was absent, that is the friction was equal to 0, then what would have happened is, when you remove some unit sand from this system, uh, it will the pressure applied on the air will decrease, and this system will move slightly upward, and because there is no friction, it will actually oscillate. But here we have been given that there is a friction acting on the system. So what will happen is these oscillations will eventually die down, and the system will come to a steady state equilibrium. So what happens here is uh, the work done that is involved when you remove this sand, will that the net work will be equal to uh, the work done uh, in the expansion of the air, that is what we calculated as nRT ln Vf by Vi plus the work done by friction. So this is the total work done, and this is the work done by friction in damping the oscillation, and that the summation of both these works will give us the net work done by the system. So oh sorry, this will be minus here, and so we can write this as nRT ln Vf by Vi minus work done by friction. So uh, also another thing with no is that the W net would be equal to P ATM pressure exerted by the ATMs times delta V plus W plus omega G delta H. This is basically P delta V that has been done, and this is equal to the final pressure times the delta V, and here delta V is equal to Vf minus Vi. So what we do now is that we equate this W net, we substitute this W net in this equation here, and what we'll get is we'll get the work done by friction is equal to minus nRT ln Vf by Vi plus Pf delta V, and this is equal to integral Vi by Vf. That we are just writing, we are just reconverting this equation into an integral. So that is minus P dV plus Pf delta V. So we can then further write it as integral Vi to Vf Pf minus P dV. So what happens now is, suppose you remove a very small amount of sand from the system, that is delta W tending to 0. What will happen is the system will move very slightly up, and because it is moving very slowly because of the very small removal of sand, the work done by the friction uh, will be approximately like tending to 0. So we can say that when we remove the sand grains one at a time, that will lead uh, to the most efficient removal of like most efficient conversion of work. So since there is no heat energy that is lost as frictional work. So basically this is the final equation uh, that you get, that is W friction is equal to so, and you can do it for example here I guess it's asked that what will happen if you remove in two blocks, that is W by 2 and W by 2. So you can integrate this equation from W to W by 2 and then W by 2 to 0. So that is how you will get the total uh, work involved in the loss as heat in the friction. um, like if I hope it's mostly clear. If it's still not clear, like we'll send the solutions for the quiz so that you can refer to it in your own time. And if you have any doubts, still like, you can feel free to like ask me again. So apart from this, another thing. we're already um, like way over time. So I'll just go briefly over the questions from the midsem. So here um, we have the following questions. Uh, what do you understand by the term reversible process, and how can a process be made reversible? So uh, a reversible process is basically where the s dot gen term will be equal to 0, and this can be achieved by changing the process in very small steps. So this is what you might have studied in JE as well, that for a reversible process the steps taken to bring about change in the system should be very small. So this is the answer to that question. For the second question, explain in one or two sentences why enthalpy of an ideal gas is only a function of temperature but not of pressure. Okay, so for this we can use this relation here. Um, we know that for ideal gases PV is equal to nRT, and V can be written as nRT by P. So
V by N and V W.
so dV by dt would give you nRT nR by P, and since it is T times dV by dt, you'll get another T here, and here you'll get V minus nRT by P, and again since V is nRT by P, this term cancels to be 0, and you get dH as CpdT. So this shows that for a ideal gas, the change in enthalpy is only a function of temperature and not of pressure. So basically, whenever you are asked to prove something that might be related to ideal gases uh, and some state function, for example, even if you have to do it for U, suppose you have to prove for U that for an ideal gas it is only a function of temperature. What you do is you substitute P as nRT by V, and then you further simplify, you will get that this term tends to goes to 0, and we'll get du is only as a function of cv dt. Okay, so for the next question, derive an expression for the internal energy of the ideal gas in terms of temperature and pressure. um, okay, so we know that for the C part, we know that H bar is equal to Q bar plus PV bar, and for ideal gases, H bar is equal to U bar plus RT. That is, we are just substituting this as PV with RT, uh, and PV bar with RT. So also we know that DH is equal to CP dt for an ideal gas. So H H as a function of T would be given as the enthalpy at reference temperature plus integral T R to T Cp dt, and so we'll get H T is equal to uh, okay, oh okay, sorry. Okay, so let me start again. So H bar is equal to U bar plus PV bar. Using the nRT by nRT equation, so PV is equal to nRT. We get the U bar is equal to H bar is equal to U bar plus RT, and DH is equal to CP dt. So we can write DH is equal to DU plus um, RDT, and then uh,
Yeah, just to move forward from there. Yeah, so now you just substitute this expression for h from here. So you get u is uh, integral cp dt tr to t minus rt. I mean, just like it feels like fairly straightforward here. It's a bit odd question actually. So yeah, let's just moving forward.
okay. Um,
point.
Okay. So the Van der Waals equation of state is written as P plus A by V bar square. V minus B is equal to RT. Derive an expression for isothermal compressibility. So I'll not go into much detail for this question because this is basically like we know that isothermal compressibility, K is equal to 1 by V bar dV bar by dP at t. So in this equation you hold t constant and you differentiate this entire equation with respect to p, and you'll get a expression for dv by dp at t, and you can basically substitute that equation in this formula and you'll get an expression for k. So that is all you have to do here. That's just a basic differentiation. It shouldn't be too difficult. Then for the next question, for a substance that obeys Van der Waals equation of state, we find that the substance cools during isenthalpic expansion. Using this information, can you comment on whether dH by dt will be positioned positive valued or negative valued or equal to 0? Provide justification. So what you do is you have been provided with um, okay, you have been provided with this equation here. So for an isenthalpic process, this will be equal to 0, and you can write dt by dp as v minus t dou v by dou t at p upon uh, minus cp. So this is the equation that we get for dt by dp, and it is asked that um, can you comment on whether dH by dP will be positive valued? So this is at constant enthalpy. Uh, uh,
Expression for dH by dP is the same, so it's going to be positive.
um, okay, I'm a bit confused about this. Um, so I'll just move on to the next question for now. We'll send a solution so that you can have a look. It's fairly straightforward. Um, okay. So this is another major question that we had in the midsem, and it is basically manipulation of like all the equations that have been given here. I'll solve it separately on a new page. Okay. So uh, what? Okay. So what we need to prove is we need to prove that u tp2 minus u tp1 is equal to integral v1 v2 z minus 1 p dv bar. We have the equation given that du is equal to t dp by dt p bar minus p dv. Also, since we know that z is equal to pv bar by rt and this is equal to 1 plus vp, we can write that we can differentiate this with respect to uh, uh, with respect to temperature, and we'll get dp by dt v by rt minus pv by rt square is equal to v times dp by dt at v, and this can be written as v by rt minus b dp by dt at v bar. This is equal to p v bar by rt square. Also, we can write from the z is equal to 1 plus bp equation that V by RT is equal to 1 by P plus B, and similarly PV by RT square is equal to Z by T. Sorry, Z by T. So this equation here can be simplified into T dP by dt at constant volume minus P is equal to Z minus 1 times P. So uh, now we know that we initially had this equation. We substitute this part over here, and we'll get du is equal to z minus 1 p dv. So we can integrate both sides, and we'll get that u t comma p2 minus u t comma p1 is equal to integral v1 by v2 z minus 1 p dv. So as you can see, it was not very difficult. Although when I had actually solved it during my midsem, I got pretty confused. What you need to consider is you first need to take the equation, the relation that has been given to you. You figure out how you can get this term, like the dp by dt term, and you have to use the relation given to you, that is z, in order, and differentiate it with respect to what you want. So here we wanted dp by dt, so you differentiate z with respect to t to get the required relation, and then substitute accordingly to arrive at the final answer. So because we are running out of time, like I won't be able to solve the second part of it, but it is fairly straightforward. Like it's a continuation of like it's basically continuation of this. You use this to find this. We'll send all the solutions to you on the group so that you can refer to it in your own time, and if you have any doubts, you can reach out to us. So yeah, that will be it for the TSC today.
Yeah, so I suggest like working on standard examples and obviously your tutorials as well, and that should help you especially for the exam. And I guess so. That's if any other specific questions, we'll wait for a couple of minutes. Otherwise, we're done with the session. Decent.
Okay, I fucked up a lot.
Not listening is what just ended.
Okay.